Module 6, Confidence Intervals. Welcome to the realm of inferential statistics, where we move beyond mere descriptions and begin making informed predictions and decisions. Through this module, we'll delve into the art of estimation, a technique to infer or predict unknown population parameters based on sample statistics. Let's embark on this insightful journey. Point estimate and margin of error. Imagine you're trying to determine the average height of students in a university. Taking the height of a few students, a sample, and calculating the average gives you a point estimate. This estimate is a single value that represents a population parameter. However, your sample might not perfectly represent the entire population, leading to some error. That's where the margin of error comes in. It gives a range within which the true population parameter likely falls. For example, suppose from a sample of 100 students, we find an average height of 165 centimeters with a margin of error of 3 centimeters. This means we're confident that the true average height of all students is between 162 and 168 centimeters. Confidence intervals for the population mean. A confidence interval provides a range of values used to estimate the true population parameter. It is constructed around the sample statistic and includes the margin of error. The level of confidence represents the frequency, percentage, at which the confidence interval contains the true population parameter. For example, if you have a 95% confidence interval of 162 to 168 centimeters for our students' average height, it means that if we took numerous samples and built an interval for each of them, we expect about 95% of those intervals to contain the true average height. When calculating the standard deviation to use as the standard deviation of an entire sample, you need to divide the standard deviation of the sample by the square root of the sample size. We'll discuss an example a bit later. T-distribution and T-table. While the normal distribution is popular, it isn't always applicable, especially with smaller samples or when the population's standard deviation is unknown. Enter the T-distribution, a family of curves that look somewhat similar to the normal distribution but have heavier tails. As the sample size increases, the T-distribution approaches the normal distribution. The T-table provides critical values of the T-distribution. This distribution is generally used when 1. The sample size is less than 30, and 2. The whole population standard deviation is unknown. And 3. You're using the sample standard deviation as an estimate for a larger population. The T-table has rows and columns. The columns usually represent the confidence level or two-tailed significance level. The rows correspond to the degrees of freedom, DFA, which is typically calculated as the sample size minus 1. Each value in the table is a T-value. Here's a step-by-step guide on using it. Determine the degrees of freedom, which is the sample size minus 1. Choose your significance level, alpha. Common choices are 0.5, 0.1, and 0.10. If you're doing a two-tailed test, which means checking for deviation in both directions, use the given alpha. For a one-tailed test, you'd have the alpha. Find the t-value. With your degrees of freedom and chosen alpha, locate the corresponding t-value in the table. For example, imagine you're conducting a one-sample t-test with a sample size of 15. And want to test at the 0.5 significance level. Your degrees of freedom are 15 minus 1, which is 14. For a two-tailed test at the 0.5 significance level, use an alpha of 0.5. In the T-table, find where DF or 14 meets an alpha of 0.5. This is your critical T-value. If the calculated T-value from your data exceeds this critical value, you'd reject the null hypothesis at the 0.5 significance level. In essence, the T-table provides a reference for deciding whether a given test statistic is extreme enough to be statistically significant. Given its centrality in inferential statistics, understanding and using the T-table is a foundational skill for any statistician or researcher. Point estimate for population proportion. Just as we can find a point estimate for a population mean, we can find one for a population proportion. If we sampled 100 students and found that 60 of them prefer online learning, our point estimate for the proportion preferring online learning would be 60 over 100, or 0.6. Confidence interval for population proportions. For proportions, our confidence intervals wrap around our point estimate in a similar way to means. It provides a range within which the true population proportion likely falls. Example, if 60 out of 100 students sampled prefer online classes, and we construct a 95% confidence interval of 0.50 to 0.70, we're confident that between 50% and 70% of all students prefer online classes. Determining minimum sample size. The sample size significantly influences the accuracy of our predictions. When estimating either a mean or proportion, we can determine the minimum sample size required to achieve a desired margin of error at a certain confidence level. Example, if you wanted to estimate the proportion of students who prefer online classes with a margin of error of just 2% at a 95% confidence level, there's a specific sample size that meets this criteria. You'd calculate it using formulas tailored for either means or proportions. Let's look at a couple of examples. A random sample of 20 students has a test score with a mean of 81.5 and sample standard deviation of 10.2. Construct the confidence interval for the population mean to a confidence level of 90%. Here are the given data. Sample mean is 81.5. Sample standard deviation is 10.2. Sample size is 40. Confidence level is 0.90. First, you need to divide the sample standard deviation by the square root of the sample size. 10.2 divided by the square root of 19 is about 2.34. Next, find the t-value corresponding to the desired confidence level and degrees of freedom. For a 0.90 confidence level, the significance level, the alpha is 1 minus 9, which equals 10. Since it's a two-tailed test, the significance level for each tail is 5. Using a t-table and looking up a df of 19 and an alpha 0.5, we find t equals 1.729. Now, we can calculate the standard error by multiplying the 1.729 by the 2.34 standard deviation. That gets us about 4.5. The sample mean was 81.5, which makes our confidence interval 81.5 plus or minus 4.5. The confidence interval is this between 77.45 and 85.55. We can be 90% certain that the real mean of the general public taking this exam will be between 77.45 and 85.55. Of course, that doesn't say anything about what any individual score might or might not be. Another example. Construct a 99% confidence interval for data set A. Data set A is 5.8, 6.8, 8.7, 5.7, 5.8, 8.2, 7.1, 7.0, 6.9, and 8.3. Okay? First find the sample mean, which you do by adding them all up and dividing by 10, the sample size. This gets you a sample mean of 7.3. Next, get the standard deviation using Excel or the formula. This gets you about 1.09. Then we can divide by the square root of 10, giving us 0.344. For 9 degrees of freedom and a 99% confidence level, the t-value is approximately 3.25. Multiplied by 0.344, that gets you about 1.12. So, the confidence interval is 7.03, plus or minus 1.12. In conclusion, inferential statistics is about making educated guesses, but these aren't wild stabs in the dark. Through the methodologies covered in this module, we can make well-informed, statistically backed decisions and predictions about entire populations based on just a sample. It's a powerful tool in the world of statistics. Next, we'll use these sample principles of venture into hypothesis testing.